Welcome back to the next video, everybody. Today we're going to continue on further into chapter 8, looking at deformation theory. Today we'll be looking at coefficient rings and where Galois representations might occur in the wild. Just some examples. Okay, so recall, based on the content of last video, we're led to study continuous homomorphisms rho from GKS to GLN of A, where A is some topological ring, N is a natural number, and GKS is the Galois group of K bar S, the maximal algebraic extension of K and K bar unramified outside a finite set of places S. So the first question becomes, which A do we care about? Which topological rings do we actually care about here? The answer turns out to be coefficient rings. A coefficient ring A is a complete Noetherian local ring A with finite residue field K of characteristic, let's say, P. The point is that A has a natural profinite topology given by the M-adic topology, in which a base of open ideals is given by the powers of the unique maximal ideal MA of A. So in this way, A has a topology on it similar to the Kroll topology on the Galois group. This seems like a natural choice. Okay, so A is the inverse limit over integers V of A mod Vth powers of MA. Okay, so what's once you have an object in mathematics, you want to know what the correct morphisms between those objects are. What's the correct notion of a homomorphism of coefficient rings? A coefficient ring homomorphism is just a continuous homomorphism of coefficient rings A prime to A, such that the pre-image of the maximal ideal of A is the maximal ideal of A prime. Another way of saying that is that the induced homomorphism on residue fields is just an isomorphism. Okay. Now, if A is this is just kind of a technical remark. If A is a coefficient ring of residue characteristic, let's say P, then P is topologically nilpotent in A. That is, the sequence of powers of P converges to 0 in A. You can check this. So there's a natural ring map from the p-adic integers to A. I've talked about this before, but let's review this. So we know there's definitely a natural ring map from Z to A. And you know that under this map, the ideal P to the NZ maps to the ideal P to the NA. So that gives me morphisms from Z mod P to the NZ to A mod P to the NA, and these are compatible. So they provide a morphism of projective systems and hence a morphism between the inverse limits over these guys over N. Okay, but the inverse limit of Z mod P to the NZ is Z sub P, p-adic integers. But A is P complete because it's a coefficient ring. So the inverse limit of A mod P to the NA is just A. So there's your map from ZP to A. Okay, now this map here isn't necessarily a coefficient ring homomorphism, which might, for technical reasons, provide some problems with our theory. It would be a coefficient ring homomorphism if K, the residue field, was just the prime field Z mod PZ, right? So the way around this is to introduce the ring of Witt vectors of K, W sub K, W of K. This is the discrete valuation ring extension of Z sub P, which is absolutely unramified, which means there's no ramification of a uniformizer, okay, and which has residue field K. So, I mean, it's not easy to show that what Witt vectors even are, that the ring of Witt vectors exists, but okay, but they do, and we won't go too in depth into this because it just doesn't matter for us that much. So any coefficient ring A with residue field K is equipped with a continuous coefficient, actual coefficient ring homomorphism from the ring of Witt vectors of K to A, and this is the identity on residue fields. So if K isn't the prime field FP, you can replace this map ZP to A by the map from W of K to A. And then you've got yourself a natural coefficient ring homomorphism sort of derived from the setup in front of us. Okay, so GLN of A. So once you give A the M-adic topology, GLN of A then carries the corresponding profinite topology, because you can think of GLN of A as the inverse limit over V of GLN of A mod M to the V sub A, where a basis of open normal subgroups is the multiplicative group of N by N matrices with coefficients in A, such that when you reduce them mod a fixed power of MA, you get the identity matrix. So very similar to the M-adic topology on A, but kind of applied to the group GLN of A. All right. So from here on out, a continuous homomorphism rho from some GKS to GLN of A, where A is a coefficient ring, will be called a Galois representation of degree N, or of dimension N. Okay. Are these natural? Well, we already know the answer to this, but let's just review. Let E over K be an elliptic curve over a number field K. And for a natural number N, denote E bracket N, the N torsion of E over K bar. You know the Galois group of K acts as a group of automorphisms on the K bar points of E, and this certainly induces an action on the N torsion. We also know that the N torsion is abstractly isomorphic to Z mod NZ squared as groups, and so this action gives a continuous homomorphism GK to automorphisms of E bracket N, which is of course isomorphic to GL2 of Z mod NZ. This factors through GKS, right? where S is the set of prime divisors of N and all primes of bad reduction for E. So this is like theorem 9.4.1 in Diamond and Sherman, for example, but the point here is we know where this representation is unramified. It's unramified outside of the prime divisors of N and the primes of bad reduction for E. So this will filter through the corresponding Galois group GKS. All right. We call the induced homomorphism rho En from GKS to GL2 of Z mod NZ the N torsion representation attached to E, or as I've been calling it, the residual or mod N representation attached to E, although N is usually a prime number, but okay. You can pass to the inverse limit of all these mod N representations as N ranges over the natural numbers, or as N ranges over the directed system of all powers of a fixed prime P, to get two other Galois representations attached to E. Rho sub E from GKS to GL2 of the profinite completion of Z hat, and rho sub EP or rho sub EP to the infinity. I think this should just be rho sub EP personally. It depends on which book you use. From GKS to GL2 of ZP, the p-adic integers. So this would be the p-adic representation attached to E. Okay. Yeah, so Silverman 1 talks a little bit about this, for example. Okay. So we've been focusing a lot in this series of talks on this representation and on the first representation when N is a prime. We don't typically do too much with this guy, although it comes up in some of Sayre's work. Okay. More generally, if I give you an abelian variety of dimension G over a number field K, you can obtain through Galois action on N torsion a degree T2G representations with coefficient rings Z mod NZ, Z hat, and Z sub P just in the same way. Okay, so basically this 2 turns into a 2G up here. Okay, if our abelian variety has complex multiplication over K, meaning its endomorphism ring is larger than Z, you may get Galois representations over other coefficient rings. We'll talk a little bit about this in chapter 17, but we won't do too much with this. Okay, so next time we'll be looking at group rings and group actions and things like that. So I'll see you then. Thanks for watching.